All right, it looks like we're all here. Is the sound working? Okay, good. All right, just making sure. Sometimes I've had issues with that. All right, so we might as well pick it up where we left off the other day. And so I see nobody was scared off, and you're all back. That's good to know. All right, so we were almost, but not 100% done with chapter 5A. There's just one more topic that needed to be finished. And then when we're done with that, we'll start with 5B. Now, today I do have two fun videos for us to watch, and we'll get to them soon enough. Don't worry, but you'll appreciate them. They're very interesting. They both involve zero. Now, you might not think zero is such a cool number, but it actually is a very cool number. And I'm sure we could find plenty of other videos about zero too if we really needed them. But these two will be particularly interesting because one of them is the history of zero, and the other one explains in very great detail exactly why you cannot divide by zero. In the past, you're always just told don't divide by zero, but this video attempts to show you why. To say the least, if we allowed division by zero, it would cause a lot of chaos in math. So, but we'll see that in a few minutes. So right now, the last topic we covered was the greatest common denominator. And then the very last topic in this chapter is called least common multiple. Now, least common multiple is actually a very simple concept. Although you might remember, you probably were introduced to this at about the same time you learned about the greatest common denominator. So, but this one is a little bit more straightforward. First of all, what we have to do is remind ourselves, what exactly do we mean by the word multiple? So this is, you can see, let's say we're interested in looking at the multiples of 18. Well, all we're doing is we're taking all the natural numbers and multiplying them by 18. So these are all multiples of 18. And of course, there's many, many more. For example, we could have 5 times 18, which is 90. And we could carry on for as long as we like. These are all referred to as multiples. So for any two numbers, we may need to discover what multiples they have in common. And among these, it's often useful to know what is the least common multiple between them. All right. Now, it turns out that there really isn't a very sophisticated way of doing this. What we basically are going to end up doing is simply writing out a list of the multiples and then choosing the right one. Okay. And I know there are techniques for doing this, but I found that they're probably more confusing than they're worth. So, and for us, for our class, what we'll probably just do is use this approach where we literally just write them down until we find the ones that we're looking for. So for example, and by the way, here's an example for 24. So if you bring them together, you can see that these are the first few multiples of 18 and 24, and where right here, you can see that they each have a multiple of 72. Now, I'm sure they have other common multiples, but these are the smallest ones that they have in common. And so therefore, we say that the least common multiple of 18 and 24 is 72. And it's that simple, all right? 72, because if you look at all these multiples, the first one that they have in common is in fact 72. Now you notice here I've got the dots to indicate that there are many more, but we don't need them because we've already found what we're looking for. So if you're going to use this procedure and you can't find them, what that means is you'll probably have to write out some more of them until you find the ones you're looking for. All right. So let's try an example. 72 and 180. Well, here's a list of the first few multiples of 72. All right, and you can see again, all we've done is multiply each one by a natural number, 1 through 5. Now, some of these you can do in your head, some of these maybe not so much. That's what the calculator's for. Some people are good at doing this in their heads, and some are not. You should know which one you are. All right, so 180 looks like this. All right. By now, you should have that part figured out. I'm good at doing this in my head, or no, I'm not good at doing this in my head. If you're not, you should just use the calculator. Even if you are, you should double check with the calculator. Now we're going to line these up. Now I think it's easier to do it in 2 rows. And so then all we have to do is go through and say, well, let's see. Here we go. They both have a 360. That's nice. So therefore, the least common multiple of 72 and 180 is 360. That's it. We don't need any more of them. So that was pretty straightforward. I think you'll agree. Compared to the greatest common factor, that requires us to create those prime factorizations. This one is, you're really just multiplying numbers together. So it's pretty simple. All right, so that was it. That was 5A. Now we're ready for 5B. Now, if you recall, way back in the beginning, we defined the natural numbers. And of course, the real numbers have many other kinds of numbers as well. In particular, if you notice, we're missing negative numbers, we're missing fractional numbers, and we're missing the 0. So what we're going to do now is add to our classification of the real numbers by looking at the so-called whole numbers. So for the whole numbers, all we did was add a 0. Okay, so you can see within the set of whole numbers, we also have all of the natural numbers. And so in terms of set theory, we say that the natural numbers are a subset of the whole numbers. This little symbol means a subset of, or is a subset of. What does it mean to be a subset? It means that n is completely contained within W. Or we can think of it this way, each element, I'll move it up here, of n is an element of W. All right, so this is what the concept of subset actually means. Okay, so you can see n is completely contained within the whole numbers, which means that n is a subset of W. Every element of n is also an element of W. All right, so now the 0 makes its appearance. Now, you'll see from the video that it took a long time before people came up with this concept of 0. It's kind of, when you stop and think about it, I mean, let's face it, in early years of humanity, the numbers were just used to help keep track of how many objects you owned or whatever the case may be. Why would anybody have needed a 0 in early agricultural societies? They would not have. Okay, it was only later on that mathematicians started coming up with these ideas. Now, what we're going to do next is introduce for the first time an even more strange concept, which is negative numbers. So you can imagine how people reacted to the first time they heard about negative numbers. That's kind of an interesting idea, negative numbers. So all of a sudden we now have the integers, which for the first time we now have to go all the way up to positive infinity and all the way down to negative infinity. That's why there's 2 sets of dots, by the way. And what you're seeing here is that we not only have the 0, but now we have negatives. So what we can now claim is that the natural numbers are a subset of the whole numbers, which in turn are a subset of the integers. Remember, these these are subset symbols. I know they look like little C's, but they're supposed to be the subset symbol. Okay, now, in order to illustrate this a little bit better, we're going to lean on a diagram that you have definitely seen before. All right, I'll give everyone a minute to catch up, and then I'm going to reintroduce you to an old friend of yours. All right, so you should be excited now. I'm about to, it's like your long lost friend is going to show up now, and you're going to say, wow, where have you been? All right, is everyone ready? So I'm going to draw this now. Whoops. And as soon as I start drawing it, you might say, oh, yes, I remember. So the box will contain all the real numbers. By the way, I forgot to mention this yesterday. We often see this symbol, this cool R, is often used to represent the real numbers. Yeah, that's pretty cool. This box contains all the real numbers. Now, we're going to use circles to represent sets. This is the integers. This will be the whole numbers. And these will be the natural numbers. And so, who wants to tell me the name of this very special diagram? This is our math trivia question for the day. I'm looking at that chat room to see who remembers it first. Oh, your pride is at stake right now. Come on. Yes, it is. I'll tell you what, I'm going to give you a hint. The first letter is all right. Oh, got somebody who knows. No. Okay, not a no. It's not coming flooding back into your memory. Oh my God. Oh, too late. It's already up
Knew
there.
it.
Venn diagram. Oh, really? You've never seen this before? That's too bad because it's a very helpful way of expressing the relationships between sets. Oh my God. Well, I mean, it's possible that nobody ever showed this to you, and that would be very unfortunate. Sure, I'm sure there's other ways of drawing it, but this is a standard approach to showing the relationship between sets, and in particular, um, what it lets you easily see is how these are all contained within each other, which means that they're subsets. Now, here to me is the best analogy for these subsets. I'm going to show you a picture of a real world object that is just like this. And you've probably seen these before in the real world, I mean. Russian dolls. Okay. What's going on here with these dolls? They're all identical to each other, and yet each one fits inside the next one. So, in other words, when you open it up, there's the next one, and then the next one, and the next one, all the way down to the smallest doll. They're all, each one is contained. So, this doll is a subset of this doll. And this doll is a subset of this doll. And it works its way all the way down to the smallest doll. Well, if you never saw those before, well, now you know what Russian dolls are. Okay. They're cool. They're all subsets of each other. So it's like a mathematical teaching tool as well as a very cool toy, I guess. But people have these in their homes. You can buy, you can spend a lot of money on these things. But they originate in Russia. And so that's why they're often called, now here they're not calling them Russian dolls, but I mean, that's how they're generally known. And, you go to any kind of, specialized gift shops, they'll have these. But anyway, that's what this reminded me of. So I thought you would find that interesting. So anyway, now we're going to introduce a few terms. Now, usually, in the early stages of a math class, you have to introduce terminology that And some of these you'll recognize and some of them you'll not recognize, and that's okay. So we're going to start out with the word opposites. Now, when you're talking about people, opposite people mean they have very different outlooks, they have different skills, they have different personalities. But here it just means they have different signs. Okay, so in other words, 3 and 3. 3 is and -3 have the same, what we call magnitude, but different signs. And so therefore we say that 3 and -3 are opposites. So if you tell people that you and your roommate are opposites, it doesn't mean that your roommate is the negative of you. Okay, but here that's what it does mean. Okay, is your roommate your negative? I bet he's not. Although maybe you can tell him that you think he is your negative, but I don't know. But yes, here opposite just means the sign is different. Now, the next one, everybody knows. I guarantee you there will be nobody in this room who says, "Oh, I've never seen that before." Here we go. Absolute value. Yes, there you go. What does that mean? Well, basically what's happening is you're eliminating the sign. So the absolute value of -2 is 2, but the absolute value of 2 is also 2. And that's really, it's just that simple. You're essentially just saying, let's get rid of the sign. And what's left is the absolute value. Now, this is useful for certain applications. Certain types of measurements do have a negative number, and often negative numbers are very, let's say, inconvenient. And so we may decide to just drop the negative altogether, and or else in some cases the sign is irrelevant, and so we may use absolute values. Now, if you were to draw a picture, though, this might bring back some memories. And if not, that's okay. We all have different memories. If you were to try to draw this on the XY coordinate system, by the way, who remembers, we mentioned this the other day, didn't we? Who invented the XY coordinate system? Yes, I think we did. Who remembers this gentleman's name? Now, this was only on Monday. Okay, this wasn't 20 years ago. This was Monday. Ooh, Renee. Oh, somebody's got it. Descartes. Yes. We have somebody in the class who has a good memory. Yoo-hoo. Okay, no, that's all right if you don't remember. It's that was just for your own personal knowledge, not for the class. So you use your XY coordinate system. Oh, you did? Oh, that's okay. I didn't realize. So you knew it just didn't get here in time. That's okay. It's not like I've got these massive prizes here to hand out or anything. All right. So anyway, so if you were to draw a picture of this, you might recall this from high school. It looks like a big V. Okay, actually, let me clean that up just a tiny bit. These two lines should have the same slope. Okay, that's a little better. Now, why does it look like this? Because if x equals 3, y equals 3. But if x equals -3, y also equals 3. So that's why it has this shape. And if you notice too, y can't be negative. That's why there's nothing going on here below the horizontal axis. Okay. So let's see. Oh, all right. Now, before we do this, there's one more little thing I want to remind you of. When you're looking at the XY coordinate system, you might recall that it's broken up into 4 what are called quadrants. So here's a trivia question for you. Which of these four quadrants is considered to be the first quadrant?
Or left.
Oh, are you sure? Well, surprisingly enough, it's this one. Yes, exactly. You got it right. It's the top right. You guys got it exactly right. But then where's the second one? Top left. That's right. Ooh, we got some serious math people in here. Andrew JP and Britt Trockenberg. I'm looking at you. Oh, and also Victor Sherman. I'm glad to see that. What about number 3? Bottom left. Yes, exactly. And then therefore 4 must be this one. So you see how it's kind of odd that they go in counterclockwise order. You would think that they would go the other way around, but somehow it ended up this way. Which reminds me, do you like fun trivia? Yes, you do. So I'm going to ask you this very interesting question before we get back to it. Okay, here we go. Now, we all know that clocks, we all know which way real clocks, not digital clocks, for God's sake. We all know which way the hands go on a real clock. It's actually called an analog clock, by the way. The opposite of digital is analog. So if I tell you that I'm looking at an analog clock, means a regular clock with hands and the whole 9 yards moves. I don't know how to describe this except by saying the word clockwise in this direction. Okay, so in a what we call a clockwise direction. Now, here's the big question. So, in other words, the way we define clockwise is this way. Now, when you stop and think about it, clocks could have just as easily been designed to go this way. So why do the hands go in this direction, not this way? Now, to answer this question, you have to think about what was the immediate predecessor of the clock. What did people use to tell time before clocks were invented in medieval Europe? The sun or sundials actually were used. Okay. You've all seen a sundial? Okay, just in case, let's get a picture of one. Oh, those are cool. Look at that. Now, here's the interesting question. That's exactly right. Noah, you have it exactly right. I can't actually draw on this picture, but can you see my mouse when I move it around here? Okay, the sun in the northern hemisphere moves in this direction. And where were sundials invented? In the northern hemisphere, in Western Europe. So it stood to reason that with sundials are moving in this direction, that the hands of a clock should go in the same direction because that's what everyone was used to. Okay. So therefore, when clocks were actually invented, the hands were designed to move in the same direction as on sundials. So if sundials had been invented in the southern hemisphere, the sun goes in the opposite direction. In fact, it goes this way. And so we would have had clocks going that way. But because the sundials were invented in the northern hemisphere, they went in this direction. In fact, you probably remember this from high school physics. If you watch water go down a drain, it goes in a clockwise direction in the northern hemisphere. In the southern hemisphere, it goes the other way around. How do you like that? Well, yes, of course. That's the whole point. The Earth's rotation, but we're on the opposite side of the world. So therefore, in the north, it goes this way. In the south, it goes this way. And when I say north and south, I mean north and south of the equator. Wow, did you find that interesting? Yes, you did. You can admit it. It's okay. It's cool to have this, all kinds of this esoteric knowledge. You never know when it's going to be useful to impress people. Okay. Just whip that out. Next time you got nothing to say to somebody, just say, by the way, do you realize why clocks move the way they do? And when one day, maybe when we have time, we'll start talking about why the minute hand was invented in the first place. Because minute hands were only introduced in the late 19th century. And so we'll discuss why that happened when it did. So that's for a later day. All right. Anyway, let's get back to this. And we're going to look at this concept of, now this is something you might remember, fractions. It turns out that fractions can be classified in two different ways. If the numerator is less than the denominator, and by the way, don't forget that the numerator is the one on top. If you've long since forgotten about this, the denominator is the one on the bottom. Like in these cases, you notice the numerator is smaller. And here, by the way, don't worry about the sign. 6 is less than 22. These are known as proper fractions. Okay? Proper fractions. Where that name came from, I don't really know. It seems like an unusual choice, but they are known in math as proper fractions. Now, in English terms, what is the opposite of proper? Oh, you all know this one.
Improper.
Improper, that's right, improper. So how do you suppose we're going to define improper fractions?
The numerator, oh, did you want to
Go
say
ahead.
it? Okay, the numerator is larger than the denominator?
That's right, exactly. It's just the opposite, of course. So here the numerator is greater than the denominator. And that's all that we need to know. Okay. So all fractions have to fall in one of those two categories. If they were equal to each other, then this would just reduce to an integer. Okay, then they would not be considered fractions. So it's only either numerator greater than denominator or less than. Okay, that's all we have to choose from. Now, the next one you might have not seen in a very long time. And that is when we have both an integer and a fraction combined. We call these mixed numbers. Yeah, look at those. You've got 1 and 2/23, 2 and 5/19, 6 and 1/8. These are known as mixed numbers. Now, what's interesting about the mixed numbers is that they can be easily converted into either proper or improper fractions. So let's say I decide this is awkward to deal with. Why don't I convert it into a fraction? What would I have to do? What might be a good way of converting this into a fraction?
Then the system
Division?
detail is going to net.
Well, here's what we're going to do. This is our strategy. I'm going to rewrite 1 in a very convenient way. So first of all, this is equal to 1 plus 2/23. The 1, I can write it as any fraction that I choose as long as the numerator and the denominator are equal. So let's do 23/23. Is this statement correct? Sure. Yes. And so now we're going to wind up with 23/25. Sorry, 25. Hold on. I got it backwards. Somehow I got it backwards. 25/23. Exactly. And now this is, of course, an improper fraction, but mathematicians would prefer fractions to these mixed numbers. And you can see why. This is very awkward to deal with. Your calculator will not give you a mixed number when you do any kind of calculations. And in fact, it won't even give you fractions like this. It will automatically convert it into the decimal equivalent, which in this case is approximately 1.08670. Okay, so, but you can see why for a calculator, these are all very awkward ways of expressing numbers. It's going to reduce everything to decimals. Okay. Now, interestingly enough, it used to be the case in the United States, and every country for that matter, that stock prices, until very recently, as a matter of fact, historically, stock prices were quoted as mixed numbers, such as, let's say, 103/4 or 105 and 5/16, that kind of thing. That was done for historical reasons, but now they're all decimals. It's because this is so awkward. But until fairly recently, you'd be surprised how long ago. In fact, why don't we check this out? When were stock prices decimalized? April 9th, 2001. That's not a long time ago. So compared to the history of the New York Stock Exchange, let's say, so it's only been the last 20 years that all stock prices have been reported as decimals instead of mixed numbers. So anyway, the historical reasons for this, we can get to that at another time, but it is a very interesting story. Very interesting, but sadly enough, we have real work to do here. So, yep, once again, we cannot go through it, but we will eventually. Now, order of operations, yes. Everybody knows how this works. So I'm going to make up a little chart here, and we're going to go through this together. What comes first? Parentheses always come first. Oh, sorry. Yes, you are absolutely right. What comes next? Yes, PEMDAS. This is what I'm building up to. Exponents are next. And then that's followed by?
Multiplication.
Yes. Now, multiplication and division are tied for third place, I guess you could call it. They're at the same level of precedence. And then we finish it up with what's last? Addition and subtraction. So if you take the first letters of all these words, you get PEMDAS. Did everyone, were you all introduced to this in order to help you remember? Most people were. It's a pretty common approach. Now, when you have a word like this, oh, it was, okay, that's designed to help you remember something. This word is there to help stick this in your memory. So a word like this that consists of other words has a special name. Does anyone know what it is?
A mnemonic device.
Well, mnemonic devices to help us remember, but this one specifically is referred to as an acronym. Oh my God, yes, an acronym. A word that is consists of other words, such as PEMDAS. So yes, and this is a mnemonic device which means it is designed to help us remember something important. This is maybe the only word you've ever seen that starts with MN. It's a little weird. It's a Greek word. That's why it's kind of unusual. Now, I asked the other class about this one, and many of them did not know this one. This is another acronym, actually, it's an acronym and it's a mnemonic device that you may have learned in science class. And I'm going to write it down, and let's see, for the fun of it, who knows what this refers to. Yes, these are the colors of the rainbow, specifically red, orange, yellow, green, blue, indigo, and violet, in that order. Those are the colors of the rainbow, or the prism. When you have a prism and you break up white light, this is what you're going to get. If you're not sure, check out the cover of Dark Side of the Moon. You all have that album? I bet you do. Yes. It's amazing. It's insane. It's been so long since it came out, but it's the ultimate classic. The Dark Side of the Moon. That's right. Oh yeah. All right. Well, anyway. So now, without parentheses, how would this expression be evaluated? Iconic is to say the least. So, by the way, this might be a good opportunity to get some practice with your calculator. Why don't you take it out and see if you can reproduce these results? And this will give you an excuse to check it out. Now, the square key on this calculator is in the upper left-hand corner. So how would you do this? You're going to type 3, then you hit the x squared button, and then you're going to say times 3 equals plus 4 equals, and that should give you 31. Because we're doing this first, and then the multiplication is second, and then only at the end do you add the 4. Okay, but on the other hand, what if it was written like this? Oh, now that changes everything, doesn't it? Before I didn't have parentheses, did I? No. So now what happens? This is evaluated first to give you a 7. And then you evaluate this 3 squared, and that's going to lead you with 9 times 7. And finally, you'll end up with 63. Oops. No, it is 63. Because we do the parentheses first, we square the 3, and then only at the end do we multiply them together. Yes, 19 too many. Now in your calculator, what you would do then is hit 3 squared times, open parentheses, 3 plus 4, close equals. Now, by the way, in this calculator, when you're using the parentheses, they do not show up. I don't know why they designed it this way, but you'll not actually see your parentheses, which is kind of unfortunate. But as long as you know what you're doing, you should get the right answer. Okay, so try that and see if it works. If it does, then that means you're getting the hang of it. All right. And the instructions are here too. You can see that we're doing it in this particular sequence. So the order of operations is very important. If we do it wrong, will of course get the wrong answer. Okay, now we're going to take, remember before we were classifying the real numbers, and if you look back at this box that we drew, this Venn diagram, if you notice, there's still a lot of numbers missing. All this out here is now, we still need to explain what's going on with all these other numbers in the diagram. So we're going to start out by introducing this concept of rational numbers. And hiding within that word rational, you see the word ratio, which should give you a hint as to where we're heading with this. A rational number is any number that can be expressed as the ratio of two integers. Now, here's some very basic examples. 2.4 is rational because it clearly could be written as 12/5. Okay. Negative 1.9, another easy example, because this equals negative 19/10. And of course, these are both integers. Now, it turns out, though, that it's not always easy to identify which numbers are rational and which ones are not. So we're going to learn some techniques to help us figure that out. Oh, good. All right, very good. So it's just a question of getting comfortable with that calculator. Especially, let's face it, you have that phone with you at all times. Every once in a while, when you've got nothing better to do, why don't you take it out and practice with the calculator? What else do you have to do? You don't have to look at the internet every single minute of the day. You can occasionally take a break from that and play with your math calculator. Come on, it's right next to the internet anyway. So there's no excuses. Now, usually when we define a rule in math, there's always a pretty decent chance that 0 might prove to be an exception. So we always have to wonder what's going on with 0. And this is no exception. So you're probably asking yourself right now, is 0 rational or not? Well, it turns out that 0 is indeed considered to be a rational number because it is an integer and it can be written as the ratio of a large number of different integers. So you can see this is a ratio of two integers, and therefore 0 is rational. All right, so just be aware of that 0 itself is considered to be rational. Now, in terms of English, what is the opposite of rational? Irrational, that's right. So if a rational number is a ratio of two integers, it must be the case that an irrational number cannot be expressed as the ratio of two integers. Now, here's the classic example that you're all very familiar with. It's your old friend pi. Okay. When did you see pi in high school? Mainly when you're dealing with geometry. Like if you needed to know the circumference of a circle. Pi r, where r is the radius. Oh, does that sound familiar? Oh God, yes. So pi is a very mysterious number. Now, what's important about it is that you notice there's an infinite number of digits after the decimal point, but it's not just that there's an infinite number of non-repeating digits after the decimal. That's how we know that it is irrational. It goes on and on forever. That's why these 3 dots are here. It goes on forever, but there's no pattern there. And that means it is irrational. Now, E, you may not have encountered E. E is another constant that, oh, we'll see what happens if they repeat. We'll get to that next. But I might as well tell you, and I'll spoil the surprise. If they repeat, then these numbers would be rational. Okay, so we're going to see that in a few minutes, but that's a very good question. So yes, when we go, we're going to find out in about a minute that if they did repeat, then these would be considered rational. But since they don't, they are irrational. E is you might not have run into this one before. It's like E, like pi. It has an infinite number of non-repeating digits after the decimal. This one you often see it pop up in finance. It's used to calculate interest rates. And then radical 2, everybody knows this number. Okay. Man, you've known about square roots since you were a little kid. Okay, I don't know what grade you even were taught. Probably in an early stage, maybe the 4th grade, 5th grade. It was pretty early on. Yeah, in fact, it's so long ago, you don't even remember, do you? No. So yeah, but so look at that. It's irrational. Ooh, that's a pretty scary thought, isn't it? So irrational numbers are the ones that we cannot express as a ratio. Now, it turns out that all real numbers are either rational or irrational. So watch what I'm going to do here. If you take the set of all rational numbers and the set of all irrational numbers, and remember, we're using fancy R to represent the real numbers. I'm going to do a set operation on here. What is this? What does that symbol represent in English? It's called a union. Now, obviously, it's not a labor union. Yes, you're right. You got it. Britt, you got it exactly right. It's a union. Now, what does it mean? It means you're combining the 2 sets and to a new set, which is itself the real numbers. The real numbers are a set as well. So the real numbers is a set that contains all the rational numbers and all the irrational numbers. How do you like that? So that means all the numbers have to be one or the other, but they can't be both. So there's an interesting twist. So watch this. I'm going to write this down in terms of set theory, and you're going to tell me what it means. Because I know you've seen this stuff before. So are you noticing, by the way, that since your math knowledge is being stimulated in your brain, that whole area where all this stuff is stored is starting to wake up. And it's starting to flood you with memories of all this wonderful math knowledge, isn't it? Yes, it is. It's like your math knowledge is a huge overstuffed closet. When you open that door, it all comes gushing out, doesn't it? Yes, it does. Yes, it is wonderful. All right, so we got some new things going on here. This represents intersection, which means this is a set that contains both. Whatever's in common to both belongs in this new set, but you notice there's nothing in there. This is the so-called empty set. And the way we interpret that in English is that no number can be both rational and irrational at the same time. All right, so they all have to be one or the other, but no number can be both. All right. So now here's an interesting question. Man, this stuff is getting so intense, isn't it? Let me ask you this hypothetical question. Are the integers rational? Why, yes, of course. So for example, 5 is equal to 5 over 1. Therefore, it is rational. In other words, in every case, we can simply rewrite it as itself over 1 and prove that the integers are rational. Now, this implies that the whole numbers and the natural numbers are also rational. So now we can use some of our cool set notation to show that n is a n is a subset, as we saw earlier, of w, which is a subset of the integers, which is a subset. By the way, we don't seem to have a letter for the rational numbers. I'll just write it out as rational numbers. Some books I've seen use this fancy Q, but we're not going to use that here. So in other words, n is a subset of w, which is a subset of I, which is a subset of the rational numbers. So now we're going to bring these all together and see how all these real numbers are actually related to each other with our friend. What kind of diagram was it again? From 8 minutes ago? The Venn diagram, that's right. Okay, stick that in your memory. Don't let it ever get away. So watch this. Now, how cool is this? It's, of course, a big box. But this time, oh, let's get that out of there. It's the real numbers, but now we can break it up into two pieces. These are my rational numbers, and these are my irrational numbers. And within the rational numbers, we have our Russian doll. In other words, the integer, the whole numbers, and the natural numbers. And now everything's complete. All the real numbers are represented in this diagram somewhere. Okay, and see, this big fence keeps them separated from each other. The irrationals are over here. They don't have any separate categories. On the rational side, we break them down further into integers, whole numbers, and natural numbers. Now, this can bring on some stress, and as far as thinking about it, what's interesting here is that the natural numbers are an infinite set, but so are the whole numbers, and so are the integers, and so are the rational numbers. All of these sets are infinite. And then the real numbers are also infinite. So what this tells us is that there are actually different levels of infinity. Oh no, is this getting too intense for the morning? Different levels of infinity. We will carry on. We'll think about this further in another video that we'll see later on in the semester, which talks about how can there be different levels of infinity. But there are. You can actually have an infinite set be a subset of a larger infinite set. Ooh. Oh my God. Well, okay, let's go on to something more practical before our brains explode by thinking about this. So now, as somebody raised the question, what happens if the decimals are repeating? So we're going to introduce two cases that we need to understand. If a number has a finite number of digits after the decimal, like 1.27 or 2.345, that is said to be a terminating decimal. On the other hand, if it's infinite but repeating, like something like this, this one is said to be repeating. Okay, or 0.252525. As long as there's a pattern there, we say that it is a repeating decimal. Over here, because they stop eventually, they're said to be terminating. Okay, so when we're ready, I'm going to tell you why this is important.
Can't you put a line over one of the numbers?
Yes, I'm glad you brought that up. In terms of notation, this number, let's see, can be written more simply as 0.3 with a little bar. The bar means that that 3 is repeated an infinite number of times. So the second one, with all the 2 5s, would be written as 0.25 bar. That is exactly correct. Okay, so that's obviously more convenient, and so we'll see that as we go along. Now, why does this matter? Because, let me just mention this now, all terminating and repeating decimals are rational. And we're going to prove it. Okay, we're not just going to claim it, we're going to prove it. All right, now, let's see how this works. So yeah, here's some more examples of terminating decimals. All that you need to know is that there's a finite number of decimals, digits rather, after the decimal point. These are the repeating ones. And again, all we need is a pattern. It doesn't have to be a single digit that's being repeated. It could be 2 or 3 or any number. As long as there's a pattern, that makes it repeating. And so both of these are, now, how can we prove that terminating decimals are rational? This is the easy one. Because, for example, it's always possible to write it as a ratio of some integer over a power of 10. For example, 0.8 is just 8 over 10. 0.124 is 124 over 1,000. And 0.3219 is 3219 over 10,000. So clearly, these are all rational numbers. And so any terminating decimal you may encounter can be easily converted into a ratio where the denominator is a power of 10. The challenging one is the repeating decimals. Those might not be obvious. Okay, so I'm going to show you a cool technique for doing this. We're going to start with the example of 0.88888. Okay, so let me show you how that works. Suppose we have the repeating decimal 0.88888, which can, of course, be rewritten as 0.8 bar. In order to prove that this is rational, we need to show a ratio of 2 integers. But how can we do that? All right, here's our clever strategy. Let's let n represent 0.8 bar. Or we can write it like this as well. Now, what happens if I multiply this by 10? All right, well, over here, that would be written as 8.88888, which you can see is nothing but 8.8 bar. Now, watch this. This is the clever part. I'm going to subtract. And watch what happens. Here I have 9n, but here these drop out, and I'm left with 8. So all of a sudden, look how simple this turned out to be. This messy looking value turned out to be 8/9, which is clearly a rational number. Because it's 8/9. And of course, 8 and 9 are integers. Wow, that was clever. Does everyone see what happened? I hope so. Good. In fact, here's what we're going to do. I'm going to challenge you to do the same thing. All starting to come back. Yes. Oh, wait. What did you want me to go over again? So, yes. Does everyone see what I did? So I started by defining n as the number that I'm interested in. And then what I do is I multiply it by 10. And I did that because when I subtract, I'm canceling out all the repeated decimals. I want to get rid of them. Okay, and the only way to do that is to subtract. So that what's left over are just integers. Okay. And then at the end, you've got 9n equals 8, which clearly implies that n equals 8/9. Okay, so that's our proof. Now, if you type that into your calculator, 8/9, it'll give you the same thing. Beautiful. Now, what I'm going to have you do, oh, let me just see, we have a chat. Okay, good. All right. I'm going to challenge you to do the same thing with 0.4444, et cetera, et cetera, et cetera. What is the ratio of two integers that we can create from 0.4444?
How do we determine what number we're interested in?
This is right. In other words, here, this would just be your n.
Okay.
So I want that to be converted into a ratio.
Oh, okay.
All right, does anyone have a number? What do you have? It's 4/9, exactly. Yes, it is. Watch. Well, here's why. 10n is 4.4 bar. 9n equals 4, n equals 4/9. Now, I want to show you another example because it turns out that the technique isn't always exactly the same. Here's an example of what I mean. Suppose that you have a number like this. You notice here that you've got two decimals that are being repeated, not just one. So we have to do something slightly different because if you turn this into n, which remember is 0.252525, if you try 10n, that's right, you're going to use 100 because 10n isn't going to do you any good. It's just 2.52525. And so you see, these will not cancel each other out. So what do we do about it? We're going to choose 100n. Because remember, the whole point of this is to eliminate the repeated digits when we subtract. So now I'm going to have 99n. These do drop out now, equals 25. So n is 25 over 99. So that was the trick. When two repeated decimals, you need to use 100. If you had something like this, what would you use instead of 100? You would use 1,000. Yes, exactly. Perfect. So that's the only thing you have to watch out for. Make sure that you're using the right multiple of 10. So that depends on how many decimals are repeated. But if you get it wrong, you'll notice right away that it's not working correctly. And so you might want to try the next one. Like if 100 isn't working, it often is 9. 9 is often what it ends up being. 9 causes all of this to happen. So does 3. So when you're done, you may end up with a multiple of 9 or possibly 3 in most cases. All right. Now, what comes next? Oh, you know what I think? I think it's time. The next topic is something you're familiar with, but I did promise you a couple of cool videos today. So we're going to stop right here. We're going to watch our videos, and then we can get back to our discussion about what are called roots and radicals. Okay, something you're all very familiar with. But first, we're going to have a video. Now, if you go to Moodle, it's floating around here somewhere. Oh, for God's sakes, I'll just open it up.
I don't know, like I don't. Landy would know way more.
I asked him and he was like, oh.
All right, so they're right here. So, but I'm going to, oh no, looks like I forgot to put it. All right, I'll tell you what. I just noticed it now. I remembered the other class, so let's go find them. I'll send you the link through the chat room then. Yeah, it's called What is Zero? This is the history of zero. So I'm going to send it to you right now through the chat room. And so you can watch it on your screen. And of course, I have to turn off the recording. And so go ahead and watch it. I think you'll really enjoy this one. So it's about 4 or 5 minutes long. So why don't you give that a shot?
My mom said she was doing a fucking thing and she didn't. Oh, that was so cute. My uncle said, "Are you working now, or are you working now? I'm coming through your area."
Helping Zero to gain a solid foothold across Europe.
All right, is everyone done with that one? All right. Pretty cool, huh? Who knew that the history of zero was so interesting? It took a long time to come around to that idea, didn't it? Yes, it did. Now, this next one is even more, a little more intense, but it's also a lot of fun because they're going to explain to you in great detail why we cannot divide by zero. All right, so be ready for some hardcore thinking. So first, yeah, I'm going to send that link to you. And then we can watch it. Okay. All right, there you go. Man, was that intense? Is your mind blown now? I mean, come on. Wow, you're going to spend the whole day floating around thinking about this stuff. After lunch, you'll have a very practical class, and it'll be just the opposite. Okay, I don't know what it is, but it won't be like this. Okay, so now we don't have a whole lot of time left, but we're going to at least start to dive into this topic that we just started, which is radicals and roots. Now, of course, you've all seen this symbol before. This tells you to take the square root of something, but you may not recall that this is just actually another way of saying x raised to the 1/2 power. That's what it actually means. It's just shorthand notation for x raised to the 1/2 power. Now, we've already had this discussion before. Are we allowed to take the square root of a negative number? Yes, but if we do, the result will be an imaginary number, which we will not deal with in this class. This class will focus only on real numbers, but yes, it's possible to do it, but remember that the result will be imaginary. Okay. Now, this you can do, though. You can take the square root of a positive number and then multiply it by -1. That works too. Now, everybody, I hope, is comfortable with on your calculator, by the way, the square root sign is found directly below, actually, it's directly below the square sign. It's in the sort of the far left, but in the middle row. And on your calculator, it's written like this. Now, it means the same thing. The square root doesn't actually usually show the two, but it's implied, because this, again, is simply shorthand notation for x to the 1/2 power. And also, as far as English is concerned, you can think of this as the square root of x, but you can also think of it as radical x. Okay, radical means square root in this context. All right, so now here, for example, if I take the square root of 49, I get 7. If I multiply that by -1, of course, I'll wind up with -7. All right, now, if I square a radical or a square root, I'll just end up with the original number. If I take the square root of 24 and then square it, I'll get 24. In this second case, though, when I multiply a negative number by itself, it's going to end up being positive. Just remember that. When you square a negative number, you always end up with a positive number. So here I'm 35, even in spite of the presence of this negative sign. Now, I'm going to test you right now. I'm going to show you a group of numbers, and I'm going to challenge you to tell me what they have in common. Are you ready? I guess as ready as you'll ever be, right? Yes. Now, I know that lunch is just around the corner, but yes, do your best. Okay, hold on. Here we go. What do you notice about these numbers? All right. Oh, here we go. Somebody noticed the pattern. Okay, well, no, that's a good guess though. Exponential growth is actually more, yes, that's exactly right. In other words, this is 1 squared, 2 squared, 3 squared. And now, well, now everybody can see the pattern. So these numbers are referred to as perfect squares. It's a very exclusive club. Like imagine within all the real numbers, not many numbers get to be perfect squares. So why is this relevant right now? Because it turns out that we can use this to figure out when square roots are rational. How does that come up? Let me write that right here. The square root of a perfect square is rational. And that's, I'll note in parentheses, because it is an integer. The square root of any other number is irrational. Ooh, so in other words, you don't even have to test them. Square root of 2, the square root of 3, the square root of 5, the square root of 7, etc., are all irrational. How do you like that? Because they're not perfect squares. But of course, I left out square root of 4. Square root of 4 is rational because it equals 2, which of course is rational. Interesting. Okay, I'll tell you what. This is roughly more or less where I left off with my other class. It's noonish. It's definitely lunchtime. I think you'll all agree with that. So I think, especially considering that the weekend is coming up, I've been stuffing your mind with lots of cool stuff this morning. And I think you're reaching the breaking point. So no, maybe not. But I think we've had enough for one day. We'll pick it up here when we come back on Monday. So all you have to do between now and Monday is just flip through the slides that we have and make sure you understand what we're doing. Okay, that's it. That's all you have to do. All right. So I guess I'll see you all then on Monday.
Not rushing
Thank you.
your
Thank
history.
you.
Bye.
Hey, all right, bye. Oh, I know Wi-Fi isn't always good. All right, see you all Monday.